Thanks everybody for coming. Very nice turnout for this morning session. So let's switch topics from how to mine Bitcoin to how to store Bitcoin. Right, I'm Marco. Online I'm better known as Benma. I'm a founder and engineer at Bitbox, produced the Bitbox02 hardware wallet. And this year I've spent a lot of time studying Miniscript and implementing Miniscript libraries and implementing support for it in the hardware wallet. And in the course of this, I got really excited about the possibilities it unlocks. So let's get started. There's a common saying, Bitcoin is programmable money. But what does it actually mean? So it basically means that you have the ability to program the conditions under which you can spend your Bitcoin. Let's look at what this means in practice. So whenever you generate a Bitcoin address and you receive coins on it, when you spend these coins, a program is being executed to determine if it's allowed to spend the Bitcoin or not. So the address directly encodes a program depicted at the bottom. This is a normal programming language. Well, not so normal, but it's a programming language. It's called Miniscript. And there's like operating codes called opcodes. And most generally, when you use a normal wallet, like a hardware wallet or a software wallet, you use a single signature account. And this basically means when you spend the coin, then this program is being executed. It's the check sig, which means it checks that there's an input to this when you spend Bitcoin. It's the signature, and then the whole thing executes. And when the check sig operator says the signature is valid for your key, then you can spend the Bitcoin. Okay, so slightly more complicated example is a multi-signature. Maybe some of you have used it. It means that you can spend the Bitcoin only if, for example, 2 out of 3 people have signed off on the spending of the Bitcoin. And this is how the script looks like. It's called a check multisig operator. And that operator has a bunch of inputs. First of all, number 3 here says there's 3 keys. Then there's the actual public keys. And the 2 means that we require 2 out of the 3 public keys to be signed for, and then the input will be the actual signatures. When you spend them, you have to provide the signatures, right? Okay, and then there's also this empty signature value here at the left, and this is basically just a Bitcoin bug that has existed since day one, like the operating code check multisig, like takes one too many elements. It's like a one off by 1 error, and this is a bug that can basically never be fixed. So you always, when you have to spend this Bitcoin in multi-signature, you will provide like a small empty value that basically does nothing. Okay, so Miniscript has a lot of opcodes. Like here's just some of them. I don't expect you to, we will not go into the details, but just to give you a picture of how many there are, and you can combine them to create more complicated spending policies. Now I just want to point out a few. For example, we have a check multisig we just talked about, and checksig for normal signature and multi-signature. Then a very interesting one is if, else, and if, which is kind of like a normal programming language. If you know some Python or JavaScript, it's basically you can have an if condition executes or an else condition, else clause, I mean. And then we have check sig verify, very interesting one. This is the relative lock time. So that means you can basically lock coins for a period of time, like say 90 days or a year. There's many more. So what are some examples of spending conditions you might want to do? Okay, let's say you have a 2 out of 3 multisig, but maybe in a certain scenario you want one of the keys to always be involved. Like maybe at a company, the CEO should always sign, and then maybe 2 employees, or like one of the 2 employees. And this would be like a kind of a key required, and then either one of key 2 or key 3. A super interesting one, I think, is inheritance. It's on everybody's minds. How do you inherit your coins safely? So this would be, for example, a condition like I can spend my coins at any time. I have always access. But should I be inactive for maybe a year? And only then someone else, like my kids or other heirs, could get access to the coins. You could think about improved security. Like, for example, maybe you're not so comfortable with a single signature setup. It would be good if a third-party server that you trust will co-sign with you. So, for example, there are spending limits per day. You cannot spend like if a thief comes, they cannot spend everything in one day. The server would always co-sign, but only up to a certain limit per day. But the downside, of course, is you don't want to completely trust that service. Like, what if it goes down and then you will be locked out of your funds forever, right? So then you can just append the condition that after a timeout, like 90 days, you can spend by yourself. Like, just if the service goes away, you have a fallback. So lastly, improved multisig security. There's always a trade-off. Most people use 2 out of 3 multisig because it gives you more security than a single signature wallet. But then again, you also want to have some breathing room for error. Like, what if you lose one key? Then you just want to be able to recover with only 2 out of the 3 keys. But ideally, you actually would want to use all 3 of them, right? Because this is even more secure. So you can, with Bitcoin script, express a condition where you can have both, right? A 3 out of 3. But if should you lose one of the keys, then only then, after a period of time of inactivity, it falls back to a 2 out of 3. So it's like the same security as before, but improved. Let's quickly look at the distribution of scripts in the chain, actually. What are people actually using? So this is a graph from 2015 until today. So the bottom parts, the red, the blue, and the violet, they are single signature wallets. Like, just if you use a hardware wallet like Bitbox, Trezor, Ledger, Electrum, software wallet, Sparrow, whatever, it's usually this. And this makes up about 90% of everything. Okay. There's at the bottom, at the top right, there's like this turquoise, and this is ordinals, so we'll just ignore that for now. Okay. Then there's yellow and orange, the other big part. And this is basically non-single signature scripts, like just more complicated scripts. If you look at them only, then how many of those are just normal multi-signature that everybody knows and uses, versus more complicated scripts like the ones I've been talking about before. And here you can see that out of all the more complicated scripts that are not single signature, around 90% are just multi-signature, like the up check multisig. So this is what you use when you use, for example, Sparrow with hardware wallets or something like that. Could you use the microphone, please?
And multisig due to Lightning usage?
So it's not a great increase in multisig, actually. So this is only a chart of multisig versus other scripts. But single sig is still the vast majority. Single sig is 90%. And I would say Lightning is definitely a contributor, but it's not like Lightning is not a simple multi-signature. It's actually a more complicated one with like a timeout and a hash lock and so on. So this is not present in this chart. This is only like just trivial, non-complicated multisig. Okay. So that basically means around 95 to 90% of all usage on the chain is single signature or multi-signature. So none of the really interesting scripts before that I told you about are in use. So why is that? So Bitcoin is programmable money, but the question then is, who can program it? And I want to demonstrate to you that until Miniscript, the answer was basically practically no one could program their money. But with Miniscript, everyone can do it. So is it programmable by you, like a normal user? The answer is, at the moment, no. Because you basically use, for example, a hardware wallet like the Bitbox or Trezor or Ledger, and you're restricted to using what they support, which is normally single signature or multi-signature. What if you're a software developer? In theory, you could do it because it's just a programming language, right? Anyone can study it and do it, but in practice, it's very, very difficult and it's not really done. I want to show you why. What are some obstacles for programming in Bitcoin? So first of all, it's just freaking hard. It's really, really difficult. Like, this condition for the improved multisig, it turns into something like this. I will not go through how it works exactly, but you can see, even if you're a software developer, trying to reason about like how those operators work on the keys, how the input should look like, and so on, is very difficult. Like, constructing it is very difficult. Think about it is very difficult. Just not fun for most of us. A big issue is it does not compose. Let's say you have this normal 2 out of 3 multi-signature, but then you want to like replace one key and make it like something more complicated, like 2 out of 2 in itself, right? So the key 1 turns into key 1A and key 1B, and they should like be a multisig on themselves. and the rest stays the same. But you can see the script completely changes. It doesn't look anything like before. There's no check multisig. It's a different thing. And this is a problem because let's say you have any condition and you just want to slightly tweak it for something, and then you have to start again the scratch, like the development from zero, basically. It doesn't scale at all. Another issue is you have like some condition. For example, one of two keys should be able to sign. Like there's many ways to actually program this in Bitcoin These are only 3 examples. You can do it as a 1 out of 2 multisig. You could use the Boolean OR operator. You could do something that looks a bit more complicated, but optimizes the fee in a certain sense, in certain cases. And then just constructing many options and figuring out which one is actually good and which is bad takes a lot of time. So here the last example, for example, has the benefit that if you use key 1 often and key 2 not so often, then the average field will be decreased. But try to reason about like why this is. It's very difficult. Okay, then when you have actually made a script and you want to spend it, you have to provide the witness. This is the input to the program, right? When you want to spend the coin, you have to provide the signatures or whatever conditions, whatever inputs you need to execute the program. And it turns out that you have to construct this witness in a very particular way. It's not just like saying, oh, there's like a multisig, so I just provide the signatures. No, you have to provide them in the correct order. You have to sometimes provide an empty value. Like here, for example, the first signature is used to satisfy the first key. And the empty value is kind of to not satisfy the second key because you only need one of them. But you still need to provide both values so the Bitcoin script executes. And so this is a kind of simple example, but when you have more complicated scripts, then constructing a valid witness under all circumstances becomes very tricky to do. And then a very big topic. I just copy-pasted a small reference. There's many consensus limits and standardness limits in Bitcoin, especially related to scripts. For example, I will not go through all of them, just an overview. Like scripts cannot be more than 10,000 bytes by consensus. Consensus means if you make one that is bigger, it cannot be mined. But if you use a different context, like this is for SegWit and Taproot, but if you use the SH context, which was before SegWit, then the limit is much smaller. Even very complicated to understand what it means, like script satisfactions where the total number of non-push opcodes plus the number of keys participating in all executed multis is above 201 are invalid by consensus. So if you're a script developer, you make a script, then you have to count up the opcodes, try to figure out what it means with these multis and so on, just very hard. And the problem is, if you get it wrong, you can receive the coins and you can never spend them again. So it will be locked forever. So, you know, it's not fun to start to think about Bitcoin script and then like worrying, is it actually like completely safe? It's just very, very scary. Yeah. A standardness rule, by the way, means that it can be mined, but if you make a transaction like this, it will be not relayed by peer-to-peer network, so it's very difficult to get it mined in practice. So you have spent maybe months developing your script. Now it's time to start receiving and spending, right? Not so fast. How do you use it? Can you import it into your favorite wallet? No, the wallet doesn't understand your script. So you would also have to create your own wallet. I mean, that makes no sense, right? Okay, so Miniscript fixes all these problems. I will show to you how Miniscript can enable every one of you and every developer to actually put those interesting conditions into practice. Ready? So what is Miniscript? It is a text representation of Bitcoin script. It comes in 2 parts. There's a policy language and a Miniscript language. The policy language is very easy to write and read by everybody. And the Miniscript language is used for interoperability. I will get to what this means. So Miniscript was developed by Peter Willey, Andrew Poelstra, and Sanket Kanyalkar at Blockstream Research a couple of years ago, at 2018, I think. What does it mean? So policy language is a simple expression language. It's composable. It's made of a few primitives, like in this example, there's like an OR and a PK. I will show you the whole picture of what it means. So it's used by developers and users to just create those spending policies I was talking about. This compiles to Miniscript. So it's like a high-level language. You can write in it a policy, and it will compile to Miniscript. Miniscript kind of looks similar to policy, but it is a bit more noisy. You can see like _b and s:, and so on. But if you squint a little, you can still see the original meaning. Like it's also easy to read it in the end if you kind of look over all the noisy parts. So this is used for example, making backups, importing, exporting, like interoperability, right? If you want to, for example, move your special account to a watch-only wallet or give it to your tax accountant or whatever, you can use this. And here I will just show you, we don't have to like consider it going forward, like users will never see this, even Miniscript users, but it's good to know that Miniscript basically maps directly to Bitcoin script. So it's a kind of a representation of Bitcoin script. For example, here you can see that OR _b kind of maps to a Boolean OR, and the PK maps to a checksig and so on. This is something you will not have to see, but it's just good to be aware of it. All right, let's look at the policy language. How do you actually make interesting scripts with this? There's only like really only these primitives. Like you have if you want to have a condition where a single key is allowed to spend, like a single person, for example, you use PK for public key. If two conditions should be true at the same time to spend, you use the AND. If it's a one of two, it's OR. You can also have thresholds like multisig, like 2 out of 3 conditions have to be true. But in this case, the conditions don't have to be keys. It can be any policy. Again, it's like a recursive composition. And one of the most interesting ones I alluded to before is the time lock, which is older. So it means you can only spend a coin if it is older than, let's say, 90 days or a year or something like that. Let's look at examples. It's easiest to explain it by examples, right? So normal single signature, that basically if you use any wallet today, this is the policy that's actually kind of used, right? It's the one key can spend policy. 2 out of 3 multisig, it's a threshold, then the number of conditions that have to be true, and then the conditions, which here in this case is 2 out of these 3 keys. And keys being public keys. Inheritance. So I can spend at any time, or my kids can spend after I've been inactive for a year, would be like either myself condition, or, and then 2 conditions have to be true for the other case. Like my kid can spend it, but also the coin has to be older than a year. So the number here, 52,000 something, is 1 year expressed in a number of Bitcoin blocks, and 1 block is arriving every 10 minutes, so you can easily convert like actual time to block numbers. So now this is where it gets interesting. So policy is 100% composable, which means, let's say you have this 2 out of 3 multisig, and now you want to, now I'm like one of the 3 cosigners, but I want my key to be actually an inheritance policy where if I become unavailable, my kid gets to cosign. So you have like the 2 previous examples, the threshold, the multisig, and the inheritance policy, and you can just paste one into the other, and the result is again a valid policy. So you can like build up more and more complicated policies as you need them. So threshold 2 out of 3 conditions, like key 2, key 3, or, and then like this inheritance policy, which is again myself or my kid after a time. I mentioned before, maybe like in some companies, CEO wants to always be a cosigner, but also has like employee set should be a second 2 out of 3. This is expressed as a and a require key. And then like the secondary condition is either one of 2 other keys. So this is a fun one. 3 out of 3 that turns into a 2 out of 3 after 90 days. So this is kind of a logic trick in a sense. So if you think about it, a threshold where, like a condition where 3 out of those 4 conditions have to be true either means key 1, key 2, and key 3 have to sign, which is a normal 3 out of 3 multisig. But if you remove any one of them, then it becomes a 2 out of 3. For example, key 1, key 2, and then after 90 days, right, it becomes a 2 out of 3. Or key 2 and key 3 can sign, or key 1 and key 3. So you can, of course, also write this in a more complicated way. Like the way you would normally do it is you say, and 2 conditions. One is 3 out of 3 now. Sorry, it's an or. Or 3 out of 3 now, and then 2 out of 3 combined with the 90 days. But this is kind of making a script shorter in the end, so you save on like unchained fees because the resulting script will be smaller. So I said policy is for everybody. Everyone can use it. So it's true. Like if you kind of understand the logics of those fragments, you can basically compose them yourself and write them yourself. That's no problem. But of course not. Like my mother probably will not be comfortable with this. So you can basically it enables also for tools and wallets. For example, in the screenshot we have Lugano wallet to build graphical user interfaces where you can kind of construct this in a nice way. For example, here at the top you have the primary path, and then you can add spanning paths for things that can only happen after a time. In this case, like this is the picture of inheritance, but you can like construct basically everything like this. So this is, I think, the first wallet that I know of that does this, but I expect like more to come. So let's switch gears. So that was policy until now. Let's look at Miniscript, the thing that policy compiles to, which is the representation of Bitcoin script itself. So Miniscript is a composition of fragments like or underscore b, pk, and so on, and they all, as I said, map to different different pieces of Bitcoin script. They kind of encapsulate Bitcoin script. In a sense, they overlay some structure. Like if you read a Bitcoin script, it's very complicated, but you can kind of like take it apart and combine it with those fragments, and then suddenly it becomes understandable. So here's like a abbreviated table. This is not all of the fragments, but you can see there's many more than in policy. Like by nature, for example, of Bitcoin script being able to express the conditions in many ways, you have many fragments doing the same thing. For example, a simple x, and y, which in policy is just the and x, y. In Miniscript and in script can be expressed in many ways. So here, for example, you have like 4 different ways to have ands and ors. They all have like different representations in Bitcoin script. And all those representations have different properties, like different sizes, different like witnesses, and so on. So examples. Let's look how policy compiles to Miniscript. Here I have full completeness. I will also show the script in the end, but you can basically just look at it or ignore it just for information. But the important part is the green middle layer. So the public key policy fragment just maps directly to PK in Miniscript. It's the same thing. It's a single sig. 2 out of 3 multisig. You can already see a difference. The threshold fragment, 2 out of 3, becomes a multi-fragment in Miniscript, and multi directly encodes the upcheck multisig, right? So it's 2 out of 3 keys. Inheritance example, like the policy we've seen before, myself or my kid after a year. In Miniscript becomes and or. It's a special fragment, and this and or basically has the semantics of x and y or z. In this case, my kid after 90 days or a year, and myself, right? But if you kind of study, if you have the list of all the Miniscript fragments and the semantics, you can kind of you can read this, right? I mean, it's a and or. Two out of 3 multisig where one key always has to be involved. And you can see already that it's, introducing the kind of noisy parts I alluded to before. So you have AND becomes AND V, OR becomes OR C, and those noisy parts are basically just making sure that the Bitcoin script underlying this can execute correctly. It's kind of like a encoding type properties. But as a reader of this, you can still see there's an AND and an OR, so it's readable if you kind of like look over the noisy parts. So maybe you wonder then, why do we even need the policy if Miniscript is also readable and so on? Like, why do we even have to bother with Miniscript? So the reason is that policy is actually super easy to read and to write. While Miniscript is easy to read, it's very difficult to write because it kind of is the same as Bitcoin script, just like one step above as a textual representation. So policy has like only those like couple fragments, primitives, while Miniscript has many more. So trying to figure out which one to use and so on is not fun to write, but you can still read it, so that's good. Policy composes perfectly, right? You can have the multisig 2 out of 3. You can plug in a inheritance thing. But if you do the same with Miniscript, now the 2 previous examples, right? You have the multi fragment in Miniscript and the AND/OR fragment in Miniscript. But if you try to paste it, it will not work. It will just not be a valid script. You can see that the result is a threshold again, not a multi. Like the fragment in the beginning changes. There's like the S colon for the keys. There's an N colon in before the older. So those are just making sure that the script works, but you cannot actually write this by hand. It's very difficult to get it right. Also, same with script, right? The policy, like 1 out of 2 keys, for example, it can compile to many different Bitcoin scripts as well as many different Miniscripts. Like all those 3 are valid Miniscripts for the same spending condition, but they have different properties, like different sizes and how you construct the witness is different and so on. So you don't want to actually bother with writing the Miniscript. You just write the policy and let the compiler like figure everything out and just give you one of them, and you will be happy because you know it's the most optimal one in terms of fees and size and everything. So on the flip side then, why do we even use Miniscript? Why don't we just use policy, for only policy and nothing else? Well, so you can't actually use the policy instead of Miniscript because the policy is not representing a specific script. Miniscript is representing a specific script. So if you have a wallet that has like a script and it turns into addresses, you always want to have the same Miniscript or Bitcoin script. And if you use the policy instead, there's no guarantee it will always compile to the same thing because it could maybe be optimized in the future to compile to something else. Policy is just a language that compiles the Miniscript. And if you think about it, Miniscript is just Bitcoin script, like it directly maps it, and it's necessary because it overlays some structure over the script, like with AND and OR and so on. And this is what enables static analysis, and it enables like wallets to create witnesses. And also lastly, the Miniscript is a text. You can like copy paste it, you can read it, you can understand it, and this is much easier to handle like in daily operations, right? You want to make an export to something, you want to handle text and like a binary blob encoded as hex or whatever. It's not very handy. So whenever you have a Miniscript that is compiled by policy, you can be sure that it's correct, which is a very nice property because a Miniscript has this structure with all those fragments that compose. It's very easy to perform static analysis on it. Like this is not something you do, this is something the software, the wallet does. And it automatically checks, for example, that the whole thing is valid. It turns into a valid Bitcoin script. It is correct, which means for any sort of condition that you have in there, you can actually create a witness. And also it obeys all the consensus and standardness limits. So there's no way to make a script that you can accidentally lock up funds forever. It is sound, which means if you have defined like a policy, like for example, in this case, 1 out of 2 keys should be able to sign, then you can be sure that really this policy is what you have to use. Like you can't, like no one can create a different kind of witness that also spends the money. Like this is like what you get. And it's safe in the sense of that every spending path requires a signature. Like maybe you make a policy and you accidentally forget, for example, to add a key somewhere. Like in this case, if you have like the condition either key signs or the coin is older than 100 blocks, then it actually means that in 100 blocks, anyone could spend the coin, not just you, or like there's just no signature on it. So this will also just be rejected if you try to make this. The compiler and the Miniscript analyzer will just say like, sorry guy, this makes no sense. So this is basically for completeness. I would say this is the most complicated thing we'll see today. And this is not something you do. I just want to like illustrate to you what a wallet does. Like in the beginning, I showed you that that creating a witness is very difficult by hand because the witness has to be arranged in a particular way and composed in a particular way. But because the Miniscript fragments are all well defined and have like a logical structure, it's easy for a wallet to automatically do this step. So you can basically import the Miniscript into a Miniscript-enabled wallet, and it will know how to spend the coins on it. It will know like, hey, I need your signature, I need this signature, I have to wait for 100 blocks. It can automatically do this everything and show it in a nice way. And the way it works under the hood is that every fragment in Miniscript defines for itself how it can be satisfied. For example, the PK, public key fragment, says if this condition is in there, I can only be satisfied with the signature that signs for like with the private key of this public key. So this is the satisfaction. And then higher level fragments define their satisfaction in terms of the sub-expressions. For example, and X and Y means you have to satisfy both of them. So the satisfaction of this is in itself the satisfaction of X and Y. So if you have, for example, an AND of two keys, like a 2 out of 2 multisig basically, then the satisfaction automatically becomes the two signatures. And this composes very nicely. So if you have like many like nested fragments that express a very complicated policy, the wallet can just do this kind of automatically, recursively, and figure out the witness how to construct it and what it needs. So this is a very nice property. Like this actually is the thing that makes that actually brings the statement to truth, like that you can actually program your money. You can make your spending policy, you can import it into your wallet, and you can actually start using it to receive and to spend. So if you receive, also, the question was how do you define witness? Yeah. So the definition of a witness is, this is the thing, when you spend your coin, you receive a Bitcoin, then you want to spend it. When you spend it, then this program runs, right, the Bitcoin script, and the witness is the input to this program. For example, the program says, I will execute a signature check. And if you want to spend the coin, then the input to this whole thing needs to be the signature. This is how you prove that you can spend the coin. This is what, for example, every wallet does that you use today, like a Bitbox02, for example. When you spend the coin, it will automatically provide the signature that will be the input, the witness, to the transaction, which tells like every node that this is a valid transaction. How does this look in practice? If you want to use Miniscript, what do you do? So first you get a Miniscript-enabled wallet. Lugano wallet is one of the first, maybe still the only one, but there will be more for sure. So you start by creating a wallet, and then you know before in the screenshot you see you either put in your policy by hand or you have a graphical user interface for it. But then for each key in the policy, you specify what the key is. It could be a hardware wallet. It could be like a seed phrase that you type in. And then a descriptor is generated from the whole thing, which is basically the whole Miniscript, including all the keys. So this is kind of the description of the whole account. It says to the wallet and to you what the policy is, under what conditions you can spend the money. You can use it to backup, import, export, and everything. So if you actually insert the keys, like I still use placeholders like me and my kid and whatever, but in reality, this looks a little bit more ugly. So if you actually insert the keys, those are extended public keys. Maybe you've heard of them. It's kind of the public key that a hardware wallet or a software wallet provides to represent a bunch of keys that are actually then used in the scripts for addresses. So if you use a hardware wallet, then for you it's important that you also verify the script on the hardware wallet and not trust your computer, because verifying this is very difficult. Hardware wallets like Bitbox and Ledger will show you an abbreviated form again, where the keys are just like S0, S1, so you can kind of read the whole thing without like going crazy with all the noise, and see that it's actually what you intended to be, and then the keys are actually displayed afterwards. So I have a quick video here. So this Bitbox 02, if you set it up, for example, with Liana, you can register by name a new wallet, and then you can verify the actual Miniscript that is in use. See, @1 means some key, @0 means some key, and then in the second step you can verify the actual public keys that are in use. Yeah, and like this, you have programmed your money you can now receive and spend. Right? So you have a policy, for example, the inheritance case, you can start receiving and spending. Let's go on. So you receive to the newly registered policy wallet. This is the address. Whatever you send to this address now is locked by the condition that I can access it anytime, or if I become unavailable, then my kids get access. Spending, similar. You can just, in this case, I can have access anytime, so I can just sign a transaction and spend it. So for example, my kid could have also a Bitbox or some other wallet, and if they do the same, they will not be able to spend the Bitcoin. They will only be able to do it if I don't move my own Bitcoin within like a year or so. Yeah, under the hood, the wallet, of course, just substitutes the public keys with actual keys. Like this is similar to, so this is a BIP32. This is what all wallets do. Like you have like subpaths. For every key you can generate receive and change addresses, arbitrarily many of them. So the wallet would just replace the keys, me and my kid, with actual like derivations. So not everything is rosy. There are still a bunch of problems. Like I would say, like in practice you can use this today, but there are like two main kind of open issues that are present today, and they will have to be fixed, I think. So one is, so far people have been used to backups being 24 words, 12 words, and that's it. And this only works because it's a single signature wallet, because a wallet knows how to map a seed phrase to a single signature wallet. It's only one key. But as soon as you have something more complicated, like a multisig or a Miniscript, then the wallet and yourself need to know exactly what that script is. And without it, you cannot actually recover your funds. So this becomes part of your backup. And I would say this is a big problem, because this is not compatible with backup solutions today. You cannot stamp it into steel. This requires less security because the keys in here are public keys. So when someone gets access to it, they can only see what coins you have, but they cannot spend the coins or steal the coins. But you still need to make sure to have a copy of this in digital form or in offline form, otherwise you cannot recover. And I would say an open problem here is just how to make this easy for everybody to use so there are no fuck-ups. And as a hardware wallet user, the second problem is, like, as a hardware wallet user, you don't actually trust your computer with anything, because it could have viruses and malware that try to steal funds from you. So you have to actually verify the thing on the hardware wallet itself. And obviously, it's not very easy to verify Miniscript. Like, as I said, my mother or my sister, etc., they would probably have difficulties like reading this on a hardware wallet or understanding what it means. But you have to understand the meaning, because if the computer tries some tricks, they could actually create a different policy that you had in mind, and then the coins could be locked in a way that you didn't intend to. So you actually have to understand it too, which is a big problem. And an open research problem is how to make this, how to present this in a way that everyone can understand it. Like one idea is, for example, to have predefined templates, like maybe the most important or most widely used Miniscripts could have like what they are, maybe like the decaying multisig or the inheritance case. And then on the hardware wallet, you would just show, hey, by the way, this is the inheritance use case with this key and that key after that time. This is easy to understand. But it's not easy to kind of make general. Well, it's an open problem. I would say it's solvable, but we're not quite there yet. Yeah. So if you have any ideas how to improve like the display of this information, then please reach out. So Miniscript is a very cool innovation. Innovation itself, but it also unlocks more innovation. Because before now, everyone was using multisig and single-sig. But with Miniscript, for the first time, everyone is able to do more, to add more security to their self-custody. For example, with inheritance policies or the decaying multisigs. And this is only the beginning, right? So there's like some wild ideas out there. Shout out to Salvatore from Ledger. He wrote a blog post about experimentation with the unbackdoorable single signature hardware wallet. It's a bit bold statement, right? So the idea is you have, for example, a Bitbox or a Ledger, but maybe you're worried that there's supply chain attacks, maybe the hardware wallet itself cannot be trusted. And he has created with Miniscript policy, like a kind of big complicated policy that is supposed to mitigate all dangers. In the first step, there's a multisig between the Ledger hardware wallet and the, for example, Ledger Live or whatever wallet you use on the computer. So the Ledger alone cannot spend anything or do any tricks. It is a multisig. But then you don't want to trust your computer either, because it could be you could lose your hotkey. It can happen easily. So there's fallbacks, right? The first fallback is a recovery key, then multisig again with a remote service. And if everything else fails, even after more time, then you go back to just a normal Ledger single sig, which is kind of what you started out with. So it's kind of falling back to the same thing as you had always, but added more security. So it's kind of cool experimentations. Nothing of this is deployed yet anywhere, but I'm sure Miniscript will be used to improve self-custody at some point. So 2023, this year is actually the year of Miniscript. It actually started already many years ago by those three guys, Peter, Andrew, and Sanket. But for a long time, it was kind of work in the background. Peter started the first implementation, Andrew started the implementation in Rust, then Peter started working on integrating it into Bitcoin Core in 2019. This step is very important because once it's in Bitcoin Core, it's kind of a seal of approval by the whole community. It will be maintained forever, and you can be sure if you build on top of it, it will not go away. This is a very good step for everybody to start using it. And then Peter kind of left the PR hanging. I'm not sure why, but Antoine then adopted his work. Antoine and Kevin from Wizardsadine, this is the maker of the Liana wallet. They really started pushing adoption hard, in 2022, 23. Antoine finished the work, put it into Bitcoin Core. Just a couple of weeks ago, it's released, it's live. And they also actually are, I would say, responsible for rallying the whole ecosystem for adopting Miniscript. They convinced Ledger and Bitbox us to add support. And now, because of this, you're able to use it. You can start using inheritance schemes and whatever complicated policies that suit you. Right, here's a bunch of interesting links. So this is the first Bitcoin Miniscript reference and interactive policy compiler. You should actually go to this site and you can just enter your own policies and click compile, and we'll show you the Miniscript that comes out and some statistics about how big the script is, and so on. Just cool for experimentation and as a reference lookup. And then if you want to dive even deeper into the topic, I recommend this blog post that I wrote a while ago. It's a three-parter. It's actually a very deep dive. So the third part is a full implementation of Miniscript. So you can see, you can go as low as you want to. And that's it. Thank you.